This lesson's on orbital energies, and here are the objectives. So let's imagine that we have a satellite in a circular orbit around a planet. Remember, we're always assuming circular orbits in these lessons. And we've seen previously that the centripetal force, F sub r, R for radial, is provided by the gravitational force acting between the two bodies. And we know that our equation for our centripetal force is mv squared over r, and as we said, that's provided by the gravitational attraction, which by Newton's law of universal gravitation is this. And in the previous lesson, we looked at the fact that the mass of the satellite cancels, and that tells us that any satellite orbiting above the same planet at the same distance r from center to center is going to be traveling at the same orbital speed. But now let's not cancel the masses here. Let's instead multiply both sides through by r, so one of the r's on each side cancels, and let's also multiply both sides by 1/2. So I get this. Now why am I doing that? Well, because this 1/2 mv squared is our equation for the kinetic energy of a body of mass m moving at speed v. So our kinetic energy of this orbiting satellite is equal to this expression over here, 1/2 times g big M, that's the mass of the central planet. This is big M. Little m is the mass of the satellite over r. So using this idea of the centripetal force, we've now derived an expression for the kinetic energy of the satellite. And we already have an expression for the potential energy of the satellite. This is it here from an earlier lesson. And notice that they look really similar. And if we wanted to add the two of them together, we could get the total energy of the satellite. So the total energy of the satellite is its kinetic energy, which we've just found is 1/2 times g big M little m over r, plus its potential energy. So plus a negative is minus g big M little m over r. And because you've got a half minus 1, if you imagine factoring out this part here, you end up with negative 1/2 g big M little m over r. Now all of these expressions look really similar, so let's unpack them a little bit. What we've got is that the total energy, I'll call that E total, this is the total energy right here. The total energy is equal to the negative of the kinetic energy. If you take a look at the kinetic energy over here, notice that these two are negatives of each other. So the total energy is the negative of the kinetic energy. And the total energy is also equal to half of the potential energy. So it's equal to half of the potential energy. That's how these three are related. The total energy is equal to the negative of the kinetic energy, which is equal to half of the potential energy. And you can see that by comparing these back and forth. To make this a little bit more concrete by putting some numbers on it, imagine that the kinetic energy were 100 joules. Remember, kinetic energy is always positive. Then 100 joules multiplied by this negative would tell us that the total energy is negative 100 joules. And if the total energy is equal to half of the potential energy, that means that the potential energy must be equal to negative 200 joules, because negative 200 multiplied by this half gives us the negative 100 that's over here. So that's how those would be related. Notice that the kinetic energy and the potential energy, when summed together, give us the total energy, that the kinetic energy is positive, and that the potential and the total energies are both negative. So let's just jot down some of those observations. I'm just going to rewrite the relationship from above so that we have it on screen again. The total energy is equal to the negative of the kinetic energy, which is equal to 1/2 of the potential energy. So first, as we said, the kinetic energy is always positive, and that's the case here. And the magnitude of the kinetic energy is 1/2 that of the potential energy, as we saw above in the example with 100 joules and negative 200 joules. Also, that the potential energy and the total energy are both negative. In contrast to the kinetic energy, which is positive, the potential and the total energy are both negative. Also, the total energy is the negative of the kinetic energy. As we saw above, the kinetic energy was 100 joules, the total energy was negative 100 joules. Lastly, and for this we need to look over here, the total energy increases as r gets bigger. Again, remember that r is the distance from center to center, the center of the planet to the center of the satellite, which means it requires an input of energy to move a satellite farther from its planet. So if we look at this equation up here for the total energy, we need to look in two places. First, we need to look at the r, because r is going to get bigger, and we also need to look at the negative. So here, as the r in the denominator gets bigger, the entire quotient, gmm over r, is going to go down. Now, if you have a decreasing absolute value of a number over here, that's what the half times this gives us, and you have a negative out front, then a decreasing negative number is one that's getting closer to 0. For example, -5, -4, -3, -2, -1, 0. As I decrease the absolute value of the number, I'm approaching 0. And so I'm never going to get a positive number out of this. The biggest it can be would be 0 when r is at infinity. So as r goes up and this whole thing goes down, I'm getting closer and closer to 0. I'm increasing. So again, the total energy increases as r gets bigger. Let's now look at this graphically. What I'm going to do here is I'm going to graph the 3 different energy functions as a function of r. So r is increasing as we go off to the right. Let's just remind ourselves of our 3 functions. I'll write kinetic energy, which is equal to 1/2 times g big M little m over r. And I will write in blue potential energy, which is equal to negative g big M little m over r. And in green we'll have our total energy, which is equal to negative 1/2 g big M little m over r. So let's ignore the g, m, and the m here, and notice that this is a kind of y is equal to 1/2 1 over x graph. If I graph this on my x-axis, which is what I'm doing, and graph this on my y-axis, which is what I'm doing, then I have a y is equal to 1/2 1 over x type graph. In other words, a reciprocal graph that has a vertical stretch of 1/2. Similarly here, I have a y is equal to negative 1 over x graph if I ignore this, which effectively is just going to provide another vertical stretch. And similarly for the total energy, I've got a graph that looks like y is equal to negative 1/2 1 over x, a reciprocal graph flipped upside down and then multiplied by a vertical stretch factor of 1/2. And I can ignore the g, m, and the m because they're going to provide the same vertical stretch factor to each of these 3 graphs, and I'm not going to label the axes at all here. Now, just before I graph this myself, let's take a look at the overall shapes. I've got in red here, y is equal to 1/2 1 over x. That's the red graph here. That's going to represent our kinetic energy. I've also graphed in blue, y is equal to negative 1 over x, and that's going to represent our potential energy. And then in green, I've got y is equal to negative 1/2 1 over x, and that's going to represent our total energy, the sum of the red and the blue graphs. Notice that the kinetic energy, the red, and the total energy, the green, are mirror images of each other. So graphing that ourselves now, our kinetic energy looks like a reciprocal graph with a vertical stretch factor of 1/2, so it might be something a bit like that. We said that our total energy, which we'll draw in green, needs to look like the mirror image of that. So there's an attempt at our total energy, and our potential energy is going to have y values that are double those of the total energy, and so it might look something like that. So that's a look at the 3 types of energy graphically as a function of r. Now this might help us see something that's interesting and probably kind of counterintuitive. Let's imagine that we're in a spaceship going around the Earth, and we'll imagine that we're in a circular orbit. And imagine that we had rocket thrusters on both sides of our spaceship, so we could fire them forwards. That would do positive work and increase our energy, or we could fire them backwards off the front of the spaceship, and that would do negative work and therefore decrease our energy. Let's imagine that we do the latter. We fire the rocket thrusters out of the front of the spaceship, so we are now exerting a force in this direction, even though, so our force is in this direction, even though we are moving in that direction. As an alternative, you might imagine that we run into some space debris that exerts a force in this direction as well. What that's going to do by doing negative work on our spaceship is it's going to decrease the total energy of the spaceship. As we can see here, in order to decrease the total energy, what's going to happen is that we need to decrease r. We need to move to the left here as we move down the total energy graph. That means that decreasing our total energy moves us to a lower orbit. It moves us to a smaller value of r going around the Earth. But if we do that, let's imagine we started out here at A, this was A, and then we end up at B after firing the rocket thrusters backwards or running into the space debris. So now we're in this lower orbit where we have a lower potential energy, but we actually have a higher kinetic energy. So after doing negative work, either by firing the rocket thrusters backwards or by running into some space debris, we've ended up in a lower orbit, and now we're going faster. And that can seem pretty counterintuitive. We fired the rocket thrusters off the front of the spaceship, but now we've ended up going faster. And that's because we're in a lower orbit. We've decreased our potential energy, but we've increased our kinetic energy by less. The total energy has still gone down. So that's a bit counterintuitive, and that's an example of some orbital maneuvering that you can do using this relationship between these three different kinds of energy.